Hello, everyone, and welcome to another episode of Microsoft Knowledge Nuggets here on M365 FM. I'm your host, Mirko Peters. Today's topic is one that almost everyone has heard of, but very few people actually understand. Vector databases. You've probably seen that term in articles about AI or heard it in conversations about Copilot and ChatGPT. But what exactly is a vector database? Is it just a regular database with a fancier name? Or is it something completely different? Imagine searching an e-commerce site for red jacket and getting results showing crimson coat and burgundy outerwear. How does the computer know those are the same thing? It's not matching keywords. Crimson isn't red and coat isn't jacket. Yet somehow the search engine understands they're related, and that's vector search in action. By the end of this episode, you'll understand what vector databases actually are, why they power AI Search and Copilot, and how they fit into Microsoft's cloud. We're keeping it plain English. No math, no jargon, just clear building blocks. What actually is a vector? Let's begin with the core question. What exactly is a vector? When most people hear the word vector, they picture an arrow from physics class, direction and magnitude. In computing, it's much simpler. A vector is really just a list of numbers, a one-dimensional array that represents something in a format the computer can work with. Here's a practical way to picture it. If I told you to meet me on the third floor in Wing B Room 12, those are three numbers describing a specific location. That's a three-dimensional vector telling you exactly where something is in a building. Now imagine I add more details: color of the door, size of the room, price per square foot. Each new detail becomes another dimension, so the more dimensions you build up, the more information you can capture about that thing. A car could be described by speed, mileage, price, weight, and safety rating. That's a five-dimensional vector. A product could be described by hundreds of features, which gives you a high-dimensional vector. Here's the thing. Vectors let us turn things into numbers that computers can compare. Words, images, sounds, documents, anything can become a list of numbers. Once everything is numbers, you can start measuring how similar two things actually are. Two rooms on the same floor with similar door colors end up close together in vector space, and two products with similar features cluster together too. That simple idea is what makes modern AI search possible. From vectors to embeddings. Not all vectors are the same. There's a special kind called an embedding, and that's where the real power comes in. So what exactly is an embedding? An embedding is a vector that represents meaning. A machine learning model like Azure OpenAI's text embedding 3small reads text and places it in a high-dimensional space. The model learned from billions of examples, so it understands how words relate. King and queen end up close together because they share similar context. King and coffee end up far apart because they don't. Here's what that means in plain English. When you search for red jacket, the system finds crimson coat. The embedding model recognizes that red and crimson are close in meaning, and jacket and coat are close too. The embeddings for those two phrases become neighbors in vector space. The computer isn't matching letters anymore, it's matching meaning. Now, let me give you a classic example. Take the vector for king, subtract the vector for man, and add the vector for woman. The result is very close to the vector for queen. King minus man plus woman equals queen. That might sound like magic, but it's really how the model bakes relationships into numbers. It learned that king and queen share a relationship similar to man and woman, and that relationship is encoded in the coordinates. So embedding models take your raw data, whether it's text, images, or audio, and convert it into a list of numbers that represent its meaning. Those numbers become coordinates in a high-dimensional space. Then when you search, your query gets converted into the same kind of coordinates. All you do is measure the distance between them. That's the core idea. Why traditional databases fall short. If embeddings are so powerful, why can't we just use a regular database? Let's answer that. Traditional SQL databases are built for exact matches. You write where color is red, and it finds every row where the color column literally equals red. That works great for structured data like customer names, order dates, or product prices, but it completely falls apart when you need fuzzy meaning. Try writing a SQL query that finds crimson coat when your data only says burgundy jacket. You can't, because SQL doesn't understand concepts. Traditional databases store data in rows and columns. They're optimized for joins, aggregations, and exact lookups. They don't know that car and automobile are the same thing. They don't know that excited and thrilled are similar emotions. They just match strings. And if your data is unstructured, like PDFs, images, audio recordings, or long documents, traditional databases can store it as a blob, but they can't really search its content. You'd need full text search, which still relies on keyword matching. If the user types budget report, but the document says financial summary, keyword search misses it entirely. Think of it this way. A regular database is like a filing cabinet. You need to know the exact file name to find what you're looking for. A vector database is like a librarian who understands what you mean. You can say, I need that document about last quarter's spending, and the librarian knows exactly which folder to pull, even if the folder is labeled Q3 Financial Summary. The librarian understands intent, not just labels. That's why vector databases exist. They store embeddings, those meaning-capturing vectors, and they index them in a way that makes similarity search fast. They don't replace traditional databases, they add a layer of understanding on top, and that layer changes everything. They add a layer of understanding on top, and that layer changes everything. How vector databases work. So how does this all work behind the scenes? Let's walk through the two main phases, ingestion and query. Ingestion is the setup phase. You take your raw data, product descriptions, support tickets, internal documents, whatever you have, and run each piece through something called an embedding model. That model turns the text into a vector, which is basically a list of numbers that captures the meaning. Then you store that vector in the database along with some metadata. The original text, a timestamp, maybe a category or a source URL. Now here's the clever part. If you had 1,000,000 documents, checking every single vector one by one would take forever. That's why vector databases use something called indexing. Think of indexing like creating a map of the vector space instead of knocking on every single door. Two common methods are IVF and HNSW. IVF stands for Inverted File Index. It works by grouping similar vectors into clusters. When you search, instead of scanning all 1,000,000 vectors, you only check the most promising clusters. It's like looking for a book in a library. You head straight to the right section instead of scanning every shelf. HNSW stands for Hierarchical Navigable Small World. The idea is pretty elegant. It builds a multi-layer map of your vectors. The top layer holds a few representative vectors that give you a rough sense of where things are. Each layer below gets more detailed. When you search, you start at the top, find the general neighborhood, then drill down layer by layer until you hit the exact match. It's like using a city map first, then a neighborhood map, then a street map. Each one gets you closer. The result is that you can search millions of vectors in milliseconds. That's what powers real-time AI features. When you type a question into a Copilot and get an answer back in seconds, somewhere a vector database just ran a similarity search across thousands or millions of documents. The query phase works the same way in reverse. You type your question. That question gets converted into a vector using the exact same embedding model. Then the database finds the nearest neighbors to your query vector using the index. It returns the most similar results ranked by distance. The closer the vectors, the more relevant the result. The Microsoft ecosystem, where vectors live. So where does all this live in the Microsoft world? The short answer is everywhere. Microsoft is adding vector capabilities into the data platforms you already use, instead of pushing you toward a separate specialist database. Let's walk through the main ones. Azure AI Search is the most common vector store for enterprise RAG. That's Retrieval-Augmented Generation. It supports hybrid search, which means it combines traditional keyword matching with vector similarity. Why does that matter? Because some searches work best with keywords, exact product codes, names, dates, while others need semantic understanding. Hybrid search gives you both. Azure AI Search also includes integrated vectorization, so you can set up a pipeline that automatically chunks documents, generates embeddings, and indexes them without writing custom code. Cosmos DB now has native vector search with diskAN indexing. diskAN stands for disk-based approximate nearest neighbor, and it's built for sub-20 millisecond latency even at massive scale. That's great for operational data that already lives in Cosmos DB. Say you're building an e-commerce app with Cosmos DB as your backend. You can now add vector search directly to your product catalog without moving data to a separate service. A customer searches for lightweight summer shoes, and your app finds products with similar descriptions, all inside your existing database. SQL Server 2025 and Azure SQL Database have joined the party too. They now include a native vector data type and functions like vector search. That means you can store embeddings right alongside your relational data. Customer records with vector representations of their preferences, inventory items with vector descriptions, support tickets with vector embeddings of their content. You don't need a separate vector database. Your existing SQL skills still apply. Just add a vector column, create an index, and start querying by similarity. Here's how Copilot uses this under the hood. When you ask, "Show me the Q3 sales report from last year," Copilot doesn't search for the exact phrase Q3 sales report. It converts your question into a vector, searches across indexed documents, emails, SharePoint files, OneDrive documents, Teams chats, and finds the document whose embedding is closest to your query. It might find a file called 2024 Q3 Financial Summary because the meaning matches, even though the exact words don't. That's vector search in action. The key insight here is Microsoft's strategy. Instead of saying, "Go buy a specialist vector database," they're adding vector capabilities to the tools you already use. Azure AI Search, Cosmos DB, SQL Server, they all speak vectors now. You don't need to learn a new system. You just need to understand the concept. And Microsoft handles the heavy lifting. Real-world use cases in AI. So where do you actually see vector databases at work today? Here's how it plays out in the real world. RAG is the big one. That stands for Retrieval-Augmented Generation, and it's how most enterprise AI runs now. When you ask a chatbot a question, it doesn't guess from its training data. Instead, it searches a vector database for relevant documents, grabs the closest matches, and hands them to the language model as context. The model then builds an answer from those actual documents. That means accurate answers about your company's own policies, products, or data. Without vector databases, the AI would be guessing from general internet knowledge. With them, it pulls straight from your real files. Recommendation engines are another huge use case. Netflix, Amazon, YouTube, they all work the same way. They turn users into vectors based on behavior, what you watch, buy, or click. And they turn items into vectors based on descriptions, reviews, and features. Then they just find the nearest neighbors. Your vector close to a movie vector, they recommend that movie. That's similarity search at massive scale, running hundreds of times per second for every single user. Semantic search is the third big use case. This is search by meaning, not by keywords. A support agent types "customer can't log in after password reset" and finds an article called "Troubleshooting Authentication Failures After Credential Updates." The words don't match, but the meaning does. That's what vector search enables. For a team handling hundreds of tickets a day, this cuts resolution time dramatically. Then there's anomaly detection, less obvious, but powerful. You embed normal behavior, typical transaction patterns, usual system metrics, standard user actions, store those vectors, then flag anything that lands far from the cluster. A transaction that looks nothing like normal, that's fraud. A server metric way outside the usual range, that's an incident brewing. Vector databases make this fast enough to run in real time. In Microsoft's world, this shows up everywhere. Power Apps uses vector search for AI suggestions when you build forms. Dynamics 365 uses it for intelligent search across customer records. Teams meeting transcripts get turned into vectors, so you can search "what did we decide about the budget" and find the exact moment in a recording. Copilot for Microsoft 365 is essentially a giant RAG system running on top of your personal and company data, all powered by vector search. Keeping it all in sync. Vector ETL. Now here's the practical challenge. Data changes, documents get updated, new products get added, old policies get archived. Every time your source data changes, your vectors need to change too. That's where vector ETL comes in. ETL stands for extract, transform, load. For vector databases, the process goes like this. First, you extract new or changed documents from your source, maybe a blob storage container, a SharePoint library, or a SQL database. Then you transform them by chunking the text into manageable pieces and running each chunk through your embedding model. Finally, you load the resulting vectors into your vector store along with metadata like the original source URL, a timestamp, and the model version used. The best practice here? Process incrementally. Don't re-embed your entire corpus every time something changes. Only process the documents that actually changed. Track which model version generated each embedding, upgrade your model, and the old vectors become inconsistent with the new ones. And watch your costs. Embedding APIs charge by token, so processing millions of documents adds up fast. In Azure, a typical workflow is straightforward. Land your documents in blob storage. Then, set up an Azure AI Search indexer with an integrated skill set that handles chunking and embedding automatically. Microsoft provides the text split skill for chunking and the Azure OpenAI embedding model skill for vector generation. The indexer runs on a schedule, picks up new files, processes them, and upserts the vectors into the index. No custom pipeline code needed. Here's a common mistake: ignoring metadata. Every vector needs its source reference, the embedding model name and version, and a creation timestamp. Without that, you can't trace where a result came from, you can't re-embed when models change, and you'll struggle with compliance audits. Treat your vectors like any other business data, track their lineage. Your next steps. So, ready to give this a try yourself? Start simple. Open the Azure portal and create an Azure AI Search resource. Then enable vector search on an existing index. Upload a few documents, pick an embedding model, and run a similarity query. You'll see it working in under an hour. For developers, grab the Python SDK, embed a handful of documents using Azure OpenAI, store them in Cosmos DB's vector search, and write a query that finds the closest match. Microsoft provides clear code samples and documentation to walk you through it. You don't have to become a data scientist to use vector databases. Microsoft's tools handle the embedding generation, the indexing, and the query logic. Your only job is to understand the concept and point the tools at your own data. Here's a challenge. Think of a search problem you deal with today. Maybe it's finding internal documents or searching a product catalog or answering customer questions from a knowledge base. Could vector search do better than keyword match? Pick a small dataset, even 100 documents, and give it a shot. You'll feel the difference right away. So now you understand what vector databases actually are. They're not some mysterious AI technology. They're just a way to store and search the meaning of your data instead of the exact words. They power the smart search and AI features inside Microsoft 365, Azure, and Copilot. Every time you ask a question and get a relevant answer, somewhere a vector database found the closest match to your query. Your structured facts, customer names, order amounts, inventory counts, those still live in traditional databases. Vector databases add the layer of understanding. They let your application search by meaning, by intent, by context. That's the big picture. Subscribe for more plain English breakdowns of Microsoft technology. Next time, we'll look at how RAG pipelines actually work and how you can build one in an afternoon. Thanks for listening.